in some sense, follow up a little bit on themes and bridges mentioned by Yao Yang. So I'll also talk about models of adversarial attacks that we may encounter in machine learning. And yeah, as previous speakers, I also decided to do pretty much a run-through, so through several recent works of mine. So I'm not going to go into details of anything pretty much, but I'll give you a little bit of an idea of the type of problems I've been thinking about and how I view these or how I approach these problems. So as I just said, we're also going to be talking about manipulations and adversarial perturbations in this talk. It's a different type of adversarial perturbations. Oh, and actually, I wanted to start with no, it should be on. Okay, so I wanted to start with acknowledging my co-authors of these works. Most of them are actually in the room. There's Shai, of course. Hassan is here, will speak later today. Tosca and Vinayak are sitting over there. Sadia is a previous former master student of mine who's not here today. But everybody else is here in the room. So the type of adversarial learning I'll be talking about is something that we've been hearing about for a long time by now. So it started now 10 years ago with this phenomenon that we train models to do really well, say on image classification tasks, but small perturbations on the instances can lead to drastic failures of these models. Right? So here, we just add a little bit of noise to a picture, flip a few pixels. To a human, it's invisible, but a machine may actually fail drastically. And this has now been worked on a lot, both in practice and in theory. Practically, often what is done is some kind of maybe combination of augmenting the training data or smoothing out a predictor after it's been trained from the learning theory perspective. Really, a variety of approaches have been taken, upper bound, lower bound, statistically, and computationally have been shown. So I'm only going to be scratching the surface here, really. So the way it's been modeled most of the time in the, I would say, kind of the PAC type of analysis or the PAC type of learning theory is to say, well, what we are doing here is we're changing the loss. If we want to be robust to adversarial perturbations, we're not going to assign loss only to misclassified instances as we do in any classification task, but also to instances such that if we perturb them a little bit, if we change the instance, say by a small radius, if then the predictor changes its prediction, if the predictor changes its labels, we'll also call this a loss. Right? So in addition to misclassified instances, every point in the margin area of a predictor will now also be considered or will be assigned loss. So this type of modeling really leads to a variety of issues. So what's been shown is that we get drastic gaps in sample complexity, we get gaps in computational complexity, and maybe I would say something that's pretty much really disturbing with this notion of adversarial robustness is that it's really kind of creates a conflict, what's been called a conflict with accuracy. If we model adversarial robustness this way, then we get an issue between deciding if we want to optimize for accuracy or this type of robustness. So the PAC type of learning theory, one of the earlier works that I would say has created lots of follow-up works was a paper that received a Cold-Best paper award by Montesa et al. 2019. So they showed this phenomenon that if we do a VC type of analysis with this type of loss, we may get drastic gaps in sample complexity for proper learning, actually. And they also showed a general positive result. They showed how we can adapt compression type of results to this type of loss. But very simple, and this has been observed many times, not obviously not just by us. Is this issue that we really are now creating an issue with accuracy, right? So if we kind of very finite situation, we have a positive and negative area. If we're optimizing with respect to a robustness parameter that's a little bit too large, then here the specifier does perfectly well in terms of classification, but in terms of robust loss, as maximum possible robust loss, whereas this classifier that keeps a distance just from all the data points misclassifies half the space, but it's still better in terms of robust loss, right? So what that means is if we optimize for one of these loss functions, we're actually badly inconsistent with respect to the other loss function. Right, so when I started getting into this area, first thing I did was with one of the first, it's not the first thing, but one of the earlier considerations in my student Sadia was to say how would we actually, or how should we actually model this type of adversarial perturbation, right? So one thing one can show, and it's been shown by many people, by many works, is that if the data is nicely separable, then there exists a robustness parameter that one can choose small enough such that this inconsistency between the two losses is not going to happen, and one can actually generalize this. If we don't want to only talk about distributions that are so nicely separable, when we did this work, we introduced a notion called a margin rate, which measures the amount of mass close to the decision boundary. One can show that if the labels are deterministic, actually, even if they're close, then one can choose an optimal robustness parameter in terms of this margin rate, such that these inconsistencies won't happen. But as soon as the labels are not deterministic, that's actually already not true. So there's really an issue with choosing a fixed robustness parameter and optimizing with respect to that. Again, as I already just said. And another issue is that if there's kind of different types of margin or different types of separability in the space, then maybe we really just don't want to optimize with respect to a fixed robustness parameter at all. Maybe we really want the robustness to be a data dependent or a distribution dependent requirement. Okay, so then, now I'm going to start running. So what we did in this work, we kind of defined in a proper way how one could phrase this loss in terms of what we call the margin canonical base predictor. So we defined here an adaptively robust loss, and we showed, as we also defined an empirical version. I'm just going to flip to this, and we showed that if we use this notion of adaptive robustness, say for a simple data augmentation scheme, then this actually leads at least very simple neural network to behave the way that we would actually like them to behave. So here, this is kind of small experiment that Sadia set up. We have data sitting on a lower dimensional manifold. In order for it to be visible, it's a one-dimensional manifold in two-dimensional space. We train the network. The network, I think, just kind of one layer running a network. On the data itself, it gets the distribution completely correct, but it cuts very close to by the manifold, introducing lots of areas of the adversarial vulnerability. If we just augment with some fixed parameter, the problem gets less entirely messed up. But if we use this notion of adaptive robustness, then we get kind of behavior in the trained predictor that we would like to see. So that's just this first notion of adaptive robustness. But an issue with this that many people bring up is that this is not a loss function, actually, right? So if I phrase my robustness requirement or my adaptive robust loss, it's not a function anymore of just an instance and a predictor, and say a label. but it relies on this margin canonical base optimal notion that I don't have access to in practice, of course. So then in follow-up works, we looked at what are other ways of relaxing this kind of rigid notion of an adversarial loss without referencing objects that we don't have control over, like this margin canonical base. Right. So skipping here. So one type of framework that I would like to mention, and this was joint work with Hassan and Vinayak, was this notion of tolerant adversarial robustness. So what we said here is, okay, maybe the true underlying robustness or optimal underlying robustness parameter is not known, but maybe we have idea of some kind of a range of what are reasonable robustness parameters to consider. And in a packed framework, maybe we can say, well, we'll evaluate our predictor with respect to one notion of perturbation set. You can think of a ball with a certain radius. But in the packed requirement, we'll compare ourselves only we will allow ourselves some slack. We'll compare ourselves with respect to the best possible for a larger perturbation radius. Right. So it turns out with this kind of relatively small change, some kind of flexibility in the notion of robustness that allowed us to derive a pack type guarantee for an algorithmic framework that is also somewhat similar to what one may want to do in practice. So visually see this method of tolerant, perturb, and smooth. So given this some kind of tolerance parameter gamma that measures how far are these two different perturbation radii apart. We set an argument that say, well, we perturb every training point with respect to a certain radius, train a predictor, and then smooth it out with respect to a smaller radius. So this is, we would argue, a much more natural algorithm than many of the methods that have led to pack type guarantees in this field of adversarial robustness. And turned out we could get in realizable case a pack type guarantee that, at least in comparison to this kind of benchmark Montesa paper, allows us to remove the potentially exponential dependence on the VC dimension. And it's for a much more natural algorithm. So allowing a little bit of flexibility for the perturbation type improved at least our understanding of what we can get pack type guarantees for substantially. So now I have to flip even more, run even faster. So we can also get linear dependence actually with a compression type of argument. So I want to mention one more maybe general concept. We can take this idea of being flexible with respect to the right notion of robustness even further. So in a work that will now actually appear at this year's NeurIPS with Tosca and Vinayak, we looked at a setup of, again, a pack type of analysis where we said, well, what if instead of one fixed perturbation type, or maybe two, we allow ourselves, or we allow the learner to have prior knowledge of the class of perturbation types. So you can think of it as maybe we know that the perturbation type should be some ball with respect to a certain norm, but we don't know what the radius is. So now we have a whole range of possible perturbation types, and we analyze in this work what type of statistical guarantees we can get in such a setup where we learn with respect to both a hypothesis class and a class of perturbation types. Turned out that if the perturbation type is totally ordered in a certain sense, then you can still get guarantees in terms of a compression type argument. In the realizable case, we also showed that if the data is not in the unrealizable diagnostic case, we actually need a little bit more. We need a little bit more resources. So in this work, we also explored two type of variations. One where we have access to an attack oracle, an oracle that can actually provide us adversarial examples. or what happens if we allow a predictor to abstain actually on perturbed instances. That can be viewed as a very natural response to what one should do or what a predictor should do when an instance has been adversarially perturbed. So there are some results in that work as well, where we allow a predictor to abstain. So I'm guessing I'm almost run out of time. So I wanted to also talk about strategic classification, but Tosca, I think, has a poster in a few hours here about this work. So I'll just skip through this. And thank you.